Today we're going to learn how to perform partial fraction decomposition. That's going to help us integrate certain rational functions that we couldn't have integrated before. So all it is the opposite of adding fractions. So we're just going to look at these two fractions and add them together as we normally would do, just to show how this is going to work. So this is easy. You get a common denominator, multiply the first by x plus 2 over x plus 2, the second x minus 3 over x minus 3, and then you just proceed. So we'll spend time doing that. It's easy. Show you though. I just want to get the result. So here's getting a common denominator. Here's multiplying out the tops, combining the top, and here's the fraction. So this is equivalent, obviously, to this sum. So what partial fraction decomposition does is just the opposite. You're going to be given this answer, and we're going to decompose it into the sum of its parts. So we're going to start with it and get the sum of its parts. So to do that, the first thing, you look at the denominator of the fraction you're given and factor it completely. All polynomial functions can be reduced to linear factors or irreducible quadratic factors. We're only going to do the ones with linear factors, so it should be pretty straightforward. So here we go. First, you notice that the bottom does factor into x minus 3x plus 2. Now, for linear factors as these, a fraction will always decompose into, so I'm going to put equal, two fractions with each of the factors. If there's more than two factors, then it would be three fractions and so on. And now the tops of these fractions will be constant numbers. So I'm just going to use a capital A and a capital B. So what we're going to do is solve for A and B, and then we'll get the partial fraction decomposition. So to do that, this whole equation, and equation is a bad word for it. It's an identity. These are exactly the same. It's not a conditional equivalence. Those are the same for any value of x. That's important. So to solve for x, we're going to multiply both sides by the common denominator, x minus 3. On the left side of this identity, the denominators are going to cancel. On the right, the x minus 3's will cancel for the a. You'll be left with a times x plus 2. And for the b, the x plus 2's will cancel. You're left with x minus 3. If you didn't see that, remember what we did was we multiplied x minus 3 times x plus 2 on both sides. So took that and we multiplied it, basically distributing it to everything, and then cancel out what cancels. You're left with gone, x plus 7. For this second one, the x minus 3's cancel. You're left with a times x plus 2, and the b term, the x plus 2's cancel. You're left with b times x minus 3. So normally you don't show that work because it's easy to visualize. So now we have to solve for a and b. And the thing I said earlier, that this was an identity and that it's true for all values of x. That's important because we can use any value of x we want to solve for a and b. So if you notice, if I chose x to be 3, the b term right here would be b times 3 minus 3, or b times 0, which means b is gone. So I'm going to do that. Let's let x be 3. We get 10 equals a times 5 plus b times 0. Therefore, a is 2. You can do the same thing to get a to cancel out. So if you look at a's term, if x were negative 2, that's going to make a term cancel out. So that's what I'm going to do. Negative 2 plus 7 is 5. A is gone. Negative 2 minus 3 is negative 5. So b is negative 1. So we found a and b, which means, let's go back up to the top. Our partial fraction decomposition is, clean this up a bit. We said a was equal to 2 and b was equal to a negative 1. So that's how that decomposes. If you look back to the problem we did right before this, we added these two fractions together, which is what we got for the decomposition. So what we just did basically was took this fraction and split it and did the reverse of that. Now, the reason why this is going to be important to do is if I ask you to integrate this, that would be very, very, very tough. But if I ask you to integrate it in this form, that's an easy natural log. That's also an easy natural log. So we're done. So that's how you do it. We'll do one or two more examples. I'll see you then.